Hello there guys, welcome back to another epic inexorable maths video. In this video we're once again looking at double integration. So we're going to do an example here, but I'm not just going to show you how to do the question, I'm going to kind of talk you guys through it as well. So this is the integral, as you can see here, from 0 to 5 of the integral from 0 to x squared of x times x squared plus y squared dy dx. So again, what this means is you need to first evaluate this kind of internal integral here, and then once you've got the value of that, you then integrate whatever this is. This will be a function of x between 0 and 5, and you integrate it with respect to x, blah, blah, blah. Now, what I'm going to draw for you guys, though, is the picture. I'm going to draw you guys the picture. This is how you do a double integral question or problem. This is how you do it. Don't ever try to draw the graph of z equals x times x squared plus y squared. Because that might be the logical thing to try and do, right? But it's too difficult. It's a 3D graph and it's really complicated to draw and it's very difficult, it's time consuming, and actually there's no reason to do it. So don't try and draw this. If you see a normal single integral, just like the integral from 0 to 1 of x squared dx, maybe something like that, maybe you will try and draw it because you need to figure out where you're integrating, and sometimes those can get quite difficult. What we're going to draw, and it's quite tricky to get your mind fully around this, but we're going to not draw this graph, but we're going to draw the region over which we're doing this integration, because that's a 2D shape. In the last video, it was just a square, but it can be more complicated, and in this question, it is. So you don't need to do this to answer this question, but you do need to do this to answer most questions. You actually need to draw the region of integration. It's like drawing the lines, you know, of your limits, x equals a and x equals b for a normal integral. It's kind of like that, but there's a lot more going on. But let's do it. So first of all, we need to realize that because this integral is being integrated with respect to y, these limits, 0 and x squared, are functions of y, which means that this is going to be y equals 0 and y equals x squared. So we need to draw those onto this graph. Again, I'm not drawing the function we're integrating. This is the hard bit. I'm not drawing what we're integrating. I'm drawing the area that we're integrating it on, okay? So y is going between 0 and x squared. So let's draw, we all know what the line y equals 0 looks like. It's just the x-axis. The line y equals x squared is going to look like this, roughly speaking. And I'm going to even label it. So this is the graph y equals x squared. Okay. So the y part of this integral is going from 0 up to x squared. So it's stopping at x squared, okay? X squared bounds it from above. Then we're integrating along the x-axis, left to right, from y equals 0 to 5. We know that these are y coordinates because we're integrating those with respect to x. So here's 0, and we'll say that 5 is about here. So what we're doing is from bottom upwards, we're bounded from 0 up to the graph x squared. So x squared stops us. Left to right along the x-axis, we're going from 0 to 5. So 0 stops us, 5 stops us, and we can see the area that we're integrating over is this area. Once again, we are not trying to find that area. The actual graph will be coming outwards, 3D, and making some sort of weird shape over here, maybe. And what we're trying to find is the volume that's kind of coming out of the graph. This is the base. This is the area that we're integrating over. So imagine this graph as a bird's eye view looking down on the function, if that makes sense. It's difficult to visualize, but this is not the function x times x squared plus y squared. It is the area that we're integrating it over. That's the thing. Okay, now let's actually do the integral. This is the integral from 0 to 5. Let's do this to here. Okay, so because we're integrating with respect to y, the x's are constant, which means we don't need to really care too much about them. So let's expand this out first of all, actually. I'll just do this up here. This will be x cubed plus x times y squared. Just so we know, I'm just going to write that up there. Okay, so let's integrate x cubed times x times y squared with respect to y. So with respect to y, x cubed is a constant, which means it will integrate to x cubed times y. Xy squared, with respect to y, will integrate to a third x times y cubed. Again, x is a constant, so you can just pretend that it's an a or a k or something like that. This is then being integrated from 0 up to x squared. This is along the y-axis, so we're going from 0 up to x squared, and you can see we're being stopped by x squared. So we're going from 0 to x squared. This is what I mean about double integration. It can get a little bit trippy because you're integrating and one of your limits is a function, but it's fine. We will not worry too much about it right now. Okay, we then work out what this is. So this is the integral still from 0 to 5. And then we substitute all of the y's for x squareds because we integrate it with respect to y. So we get x to the 5, because that's x cubed times x squared, plus a third x times x squared cubed. That's a third x times x to the 6. So a third times x to the power of 7. And then you can see if you substitute 0 in, it will all become 0. So we just ignore it. And that's dx. Okay. Cool beans. Now this, as you can see, is a normal bog standard, typical single, one variable integral. So we can just do that fairly easily. So this will become a 6th x to the power of 6 plus 1 over 24 times x to the 8. And the limits here are 0 and 5. And this would become a 6th times 5 to the power of 6 plus 1 over 24 times 5 to the power of 8. And it would be minus everything else, but of course, it's just going to be minus 0. So I'm not going to pretend that I know what this number is. I'm going to go and do it on a calculator and come back to you. So there you go, guys. It's about 18,880, give or take a little bit. Well, give a little bit, really, because it's 0.2. But that's the idea. That's the value of this. And what this represents is the volume that's bounded between the bottom of the z-axis, I suppose, and the function z equals x cubed plus xy squared on this region. This is the base of the region. And so this is the base of the region. It's kind of coming out as a rectangle, and the kind of this part, that makes sense, that's not a rectangle. It's this 3D volume, basically, you know? So imagine this is a bird's eye view looking down onto the seabed, and you're saying how much water, maybe, is right above this section of the seabed, right? I don't know. And the function is the shape that's being made by the ocean directly above it, if that makes sense. Maybe that's an analogy. But again, just to emphasize, this is not the graph of x times x squared plus y squared. This is the graph of the region that we're integrating it on. That's the subtlety. Okay, so in future videos, we will look at situations where you need to change the order that you do the integration and blah, 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 stuff like that. It's pretty interesting, it's pretty good. So stay tuned for that, guys. Hope this was helpful. As always, I'll see you in the next one.